But there are numerous things around the house that can hurt you, no doubt about that. So that's what that lab's all about, right? Getting exposed to the different acids and bases.
A relative of ours in a bucket, she was cleaning, and I think she mixed like ammonium and bleach. She mixed something.
Yeah, that's not good.
And she breathed it in, and her lungs were all scarred up.
Yeah, it's really, really bad.
She gets very, very sick very easily now because it's so.
There was a lady a few years ago tried to kill somebody for that.
Holy crap.
Tried to do what?
Killed someone from mixing household chemicals together and forming, what was it, ammonia phosphate or something out of it. It's like really, really nasty. But it's one of the reasons why you're not supposed to mix certain cleaning products together because of the gas that forms. And then when you inhale it,
Yep.
it's really, really bad.
Isn't that creepy? Like, if you don't know what you're not doing, and you accidentally put something in a bucket because you're trying to scrub something or. Holy crap.
Well, in the United States, we're really, really protected from that. I mean, if you follow the instructions, you're generally okay, but you don't really know. I know, but even I do stupid things sometimes, so, to say the least. Oh, I guess it's time to get started. So, welcome back to class, everyone. We've got a few announcements to get started. So, first and foremost, I hope everyone had a good Thanksgiving break. Did anyone do anything fun and exciting? No, nothing? All still asleep? Okay. Okay. Well, I went to Peoria and saw family, so that was not very exciting, to be honest. But that was what my vacation was. Coming up in this course, we have lecture today, and we have lecture on Thursday. Then next week on Tuesday, we have our last chapter exam. That chapter exam, it looks like, is going to be covering nuclear chemistry. I don't think we're going to get past the nuclear chemistry chapter. So you can keep that in mind when you're studying and so forth. Let's see how we do today, but I don't expect to get past the nuclear chemistry. Then, on Thursday next week, we will be getting the exam back, and then going over questions and so forth, and then reviewing. So next Thursday is set aside purely for review. There won't be a quiz, there won't be attendance or anything like that. So if for whatever reason you already have an A+ in this course and you don't feel like you have to review, then by all means feel free to do as you will. Okay. I'm not someone to encourage you to skip class in any way, shape, or form. But that being said, I just want to put it out there, attendance will not be taken at all, but at the same time, I think it's useful to review for the final. The final is going to be comprehensive, remember, so everything from probably the second day of class all the way until the last day. Okay, it's what the final will cover as we go through. So that's kind of the plan. Questions about that at all? So 2 lectures, exam Tuesday, review Thursday, and then the final and finals week. Okay. We have one more quiz we want to do, so that's not going to be today. So that pretty much tells you when that's going to be. So don't forget about that. That's what the class decided last week. We wanted to do in terms of the day. Other than that, I think the only other thing I want to mention is the last day to do work for the course is the day of the final. So I think our final is on Thursday. So midnight of that night, that will be the end to resubmit work to send work in, to do homeworks again for better scores, whatever it is, or whatever. That will be the deadline. Yeah.
Did you ever look into the homeworks?
I did look at some of the homeworks. I don't think they're overly difficult for it. I know that you mentioned that you felt that way, but I don't sort of feel that way. So I know you're not going to agree with me there.
No,
but,
it's fine.
Yep. Okay. I think that's it on this. I have, over the last few days, seen a lot of news stories about nuclear chemistry, so I thought it was kind of interesting. For example, the shield going over the Chernobyl meltdown is occurring right now. They're putting this huge shield over where Chernobyl occurred to stop the radioactive material from getting out. And also in the same terms of nuclear meltdowns, the Japanese meltdown, they're re-evaluating the cost of cleaning that up. Their previous cost expectation was 90 billion, and they doubled it to 180 billion to clean it up, which when you think about it, that's a lot of money, even for a government to spend. Switzerland last week had a vote to phase out nuclear power from their country's infrastructure and actually voted against it. So they decided not to instate a plan to phase out nuclear power, which I thought was kind of interesting there as well. Yeah. Let's see. There's one other one. Oh, I saw a news story, and I didn't really look into it very much because I didn't have time, but about taking nuclear waste and using diamonds to create power from it. And I'm not sure how they were doing it, but that just came out as well, and that would be a positive use then for nuclear waste, and actually using it to create batteries, basically. We do something similar with power generation in space. We use radiation to create power on satellites and so forth, but I've never heard of it in terms of being nuclear waste, being recycled and so forth. We talked a couple times in here about what to do with nuclear waste, and there's no good solution. So maybe, if possible, we could use it as a power source, which would be a big step in the right direction. The final thing I'm thinking of, it's kind of silly. Have you guys ever seen that? So, okay, don't make fun of me, but there's a television show called NCIS LA. It's the only NCIS I like, by the way. So don't start on the other ones. I don't watch any of them. My mother-in-law watches them all, but I like that one. Their episode last week had to do with polonium poisoning. And I think I mentioned in here how the ex-Soviet spy that was in England got poisoned by polonium. It was the exact same thing in the episode last week. The only difference was instead of putting it in tea that the actual person drank, she inhaled it from a cigarette. So I found the timing of that kind of weird with what we're talking about in class. So I think hopefully you see that this stuff is in the news and is of important interest, not just politically, but applications and so forth. I mean, we could spend 2 classes just talking about the political ramifications of nuclear power in the world today, but we won't. Okay, so back to the slides and so forth. Uses of radiation. Did we run through this last time? I think we did some of these, right? Yes, no? No? Okay.
Yeah.
Yeah, I think maybe
We were
tracers.
on the, penetration.
Oh, okay. So the idea of penetrating power and materials passing through different materials and so forth, this is important when we start talking about protecting ourselves from different types of radiation. So the key to understanding this is that the larger the particle is, or the larger the radiation is, the easier it is to stop. So, for example, alpha particles have a mass of 4. So they're actually very, very large in terms of radiation, so they're easy to stop. They're easy to get them to bump into other things and stop them. Beta particles, which is an electron, barely have any mass, so they do pass through materials relatively well. You can stop them with a thin sheet of metal and so forth. Aluminum. Foil, for example, will generally stop beta particles. Thick aluminum foil. And then gamma, really, there's no mass to gamma because it's simply energy. And because of the fact that it's energy, it's hard to stop. It doesn't have a physical presence for you to physically block it with something, so it's difficult to stop it. With gamma, we generally use lead. And you guys are aware of this, whether you recognize it or not. When you go to the doctor's office and say you're getting an x-ray on your arm, what do they make you put on? The lead vest, the very heavy lead vest. You always know it's lead because it's super heavy. That's because lead is really, really dense, and they're using that to stop stray radiation from getting into the body and so forth. The same thing occurs when you go to the dentist's office. When you go to the dentist's office and they're taking an x-ray of your teeth and so forth, oftentimes they're going to put a lead vest over you. At least my dentist does. I don't know. Does that seem weird, or does everyone do that?
It's like a little bib, it's not like a full vest.
A little
It's
bib?
like a little thing.
I think mine's the best. Well, you don't put it around. It's just
Yeah, it's
kind
Like
of
a
like
smock or
yeah, a blanket, a lead blanket. I'm going to call
a
it.
lead snow.
It depends on what type of x-rays you're getting done.
Well, it would depend. Yeah, that's possible too, depending there. I've always been curious why they don't give you a lead hat to like protect your brain. But in the end, it doesn't matter anyway, because the beam of X-rays are very tight. It's just like a little. It's like that big. So it shoots through your mouth and it doesn't go other places. It's not like it bounces off and goes in random places. Yeah.
So if you get like a CAT scan,
Mhm.
like they put you in a tube, what is it? What kind of?
CAT scans are based on MRIs, so it's a little bit more complicated. It would still fall in the gamma
Okay.
energy. It's definitely not something with a physical association to it. We're going to talk about an advancement from CAT scans called PET scans, which actually creates the radiation inside your body and then measures it, where a CAT scan, the energy is coming from out and then interacting. So I would say a CAT scan is more like an X-ray but not using X-rays, where a PET scan is one directional. If that
So
makes
when you
sense.
drink like that, like a barium, like a radioactive, is that what that is? Like a dye that
Yeah.
like, makes you like light up when they put you in a machine?
Mhm. Yep,
So
so
is
that
that-
they can see it easier.
Okay.
Yep. I don't know if anyone else has ever had to do this before, but when you go get a CAT scan of like your GI tract, they make you drink this stuff. It's gross. If you've ever done it, you know what I'm talking about. But that stuff helps them see it. And basically what it is, it's a tracer. So you take it and then they measure how that passes through your body and where it goes and so forth. And that's the general idea of it, and that's why you've got to do that. Generally, you'll drink one the night before, so it has time to get through most of your body, and then you'll drink one right away, so it kind of refreshes it as it goes through it. But yeah, that's icky, icky stuff. They actually will have radioactive material in some of those, and then they'll measure the radiation coming off as well.
Okay.
I don't know if there's multiple types or not, but I know some of them have a radioactive component to measure.
So for the
Yeah.
alpha, beta, gamma, the highest penetrating would be gamma, right?
Yep.
And then would the least penetrating be alpha?
Exactly.
Okay.
Yep. And the way that I think about this is kind of silly, but imagine that you're driving a vehicle through a parking structure. Would it be easier to get a Mini Cooper or a semi truck through the parking structure?
Maybe.
the Mini Cooper, right? It's much smaller and it can pass through easily. And same thing here. Gamma particles are much, much smaller. They actually don't have a physical presence than alpha, so they can pass through easily. Where alpha particles are huge, so that's like the semi-truck trying to get through. And it just gets blocked all the time. So it's hard to get alpha through. Like between me and you, if you had an alpha gun and you tried to shoot me, I'd probably be okay because the air particles would be enough to stop it. But gamma is so small, it would pass right through. And that's what we see. Yep. So the larger the particle, the easier it is to stop, the less material it will pass through, just like what you're saying. Now, in terms of protection from this, alpha particles can be stopped by almost anything. A piece of paper is more than enough to stop alpha particles. Beta, you're going to start getting into the metals, a little bit thicker and so forth. And then gamma, you need something relatively thick, a lead shield of some sort. X-rays, we use lead shields. Microwaves even use lead shields. So microwaves usually have a lead enclosure around the sides and back of it. And then in the front, they have leaded glass. And that leaded glass has lead inside of it, and that will absorb the radiation so it doesn't get out. That's why you need to make sure your door is always closed so that you're
Okay, so
protected.
radiation's traveling, okay, if radiation's like so dangerous,
Mhm.
it can be dangerous like if it gets in contact with our bodies and things like that. But we heat our food inside the microwave, so we're still like I don't know, what is it, the alpha particles or whatever?
It will be gamma, but
Gamma. The gamma is it'll be going through our food, right? Because it's being heated
It
in the
will.
microwave.
It does go
So
through
it's
our
still
food.
going in our bodies, it's just that it's not as much or like
okay. This is actually a really, really good, important point here. When gamma radiation or any type of radiation interacts with something, that does not make that material radioactive. So when you have a piece of food and you're heating it in the microwave, the radiation is not going into the food and sitting there and then escaping back out. It's just passing through it. And when it passes through it, that energy, actually the way a microwave works, that energy speeds up water molecules and they move faster, so it heats up the temperature.
Okay.
So it's purely heating it up through the use of radiation, not making it radioactive. The same thing with cancer treatments and so forth. If someone is getting a radiation therapy from an external source, like they're being shot with a beam of radiation, that is not making that person radioactive in any way, shape, or form. It's just interacting with the body and then leaving right away. Okay? It's not getting like soaked up into the body. Now, if they put radioactive material inside the body, like you have surgery and they put a radioactive pellet in, then you would be radioactive because you have that radioactive material in there. But just the simple treatment doesn't actually make you radioactive. So that's a really important point. We use radiation in a lot of things. Many of our foods are exposed to radiation, not just from the microwave, but from treating it before it even gets into the store. It's a relatively common practice in the United States. That does not make the food radioactive. You know, if your grandmother goes in, I always use grandmother because my grandmother went through cancer treatment. If your grandmother goes in and gets exposed to radiation to fight cancer, that doesn't make her radioactive. Okay, you know, kids can still hug her, kiss her, sit on her lap, all of that. It doesn't change anything in terms of that. So one of the biggest protective features that we have is our skin. Our skin is incredibly good at protecting us from all types of things. Radiation is no different. If you look at the three types of radiation in our skin, for example, alpha radiation, stop very easily, it's only the surface of the skin. So if you're exposed to a large amount of alpha radiation, what you actually see is burns on the skin. Okay? Radiation burning on the skin and so forth. Beta penetrates into the skin, into the inner layers and so forth, and you would have deeper types of burns where X-rays can pass all the way through. So X-rays are of particular concern safety-wise because your skin doesn't really protect you from them, and therefore your organs can be exposed to them very easily. But at the same time, they're useful in taking images and so forth. because we want them to pass through so that we can actually get an image there as well. Questions about that at all?
So how far, deep would you say the beta rays go?
Well, I'm not a biologist, so I don't know the layers of the skin.
Okay.
I know there are several layers of the skin: dermis, epidermis, subdermis, and so forth. But generally, you don't see beta radiation affecting organs inside the body because they don't get into like the chest cavity and so forth. The skin stops them before they pass into that. But I'm not exactly sure how to answer that, to be honest. I don't know the proper terminology and so forth. And some of it, or a large portion of it, should also be the amount of radiation you're exposed to. Because if, for example, let's say skin stops 99% of beta and 1% still gets through, it would make a huge difference if you're exposed to 10 millirem or a billion millirem, what actually makes it through if it's 10%. So if something does get through, then the amount becomes really important in terms of what you're actually exposed to. Did that answer your question at all?
Yeah.
Okay. I think it's the best I can do. Any other questions there? Now, in relationship to penetrating power, we do want to be aware of the opposite effect here, and that's damage to the body. The larger your radiation particle is, the more damage it can do. So think of it as being shot with something as simply as that. If it is a larger bullet, it can do more damage than a smaller bullet in terms of impact and so forth. So alpha radiation is particularly dangerous if, for whatever reason, it gets inside the body. Gamma radiation can easily get in, but it does less damage in terms of each individual particle interactions and so forth, because there's less mass associated with it. This is important for things like radiation therapy. If they're going to put a radioactive particle inside the body, they can go ahead and do alpha or beta where it's right next to it, and therefore it will cause a large amount of damage to the cancer cells, where gamma radiation can only be shot, or gamma radiation shot from the outside will only do so much interaction. Sunlight contains gamma radiation, so we want to be aware of that. And then finally, the last one is the T one that I mentioned. Did I talk about that in class at all, the Russian agent? Okay, so basically what this was an ex-Soviet spy in England, and they poisoned and killed the gentleman by putting radioactive material in his tea. It was alpha radiation, so he had to actually get it inside of his body. So by putting it into the tea and then drinking it, he took the radiation inside the body so the skin can no longer protect him, and then he died of radiation poisoning from it. It was polonium-210 was the isotope that did it. There was a really, really big story in England a few years ago when it occurred, because they shut down the airplanes in England trying to figure out how this radioactive material got into England and so forth. If it was up to me, I wouldn't have shut down the airlines because your skin's going to protect you from alpha radiation. So it'd be perfectly fine as long as you're not licking the seeds.
As far as like cancer therapy, we had cancer pretty prevalent in our family, and one of our family members was going for prostate cancer consultation. They were saying that they would use like radioactive, like little bombs. They would like inject it, and they would then go off, I guess, with inside the prostate, and then evidently it would.
Yeah, that's a form of radioactive pellets.
Right.
So basically putting it in the nice thing about that is you can put it in directly next to the cancer, and then you're only affecting the localized area. So if, for example, you're getting gamma radiation on something like in your chest, heaven forbid, then you've got to shoot through everything to do it, where this is a much more localized.
Do you think they may go with something more like that in the future, where it's just concentrated in the area that it needs to, instead of basically killing all the cells in general?
I don't know. I don't know, because it will all depend on how effective it is. If it is equally as effective, then I think yes, because you're causing less damage to the healthy cells, is the idea. But if for whatever reason it's not as effective, then they'll go with whatever's more effective.
Right.
In the end, with cancer treatment, you just want to kill it. You're not too horribly concerned about the side effects as long as you survive. That's the main thing there. So, yeah, they do everything they can, obviously, for all different types of things. Yeah. Unfortunately, I think most of us probably know somebody who's gone through cancer treatment. And especially radiation treatment is particularly common for a lot of them, so, yeah.
How do they know which type of like radiation to use? Like, is it the same one for each? Because I'm pretty sure they would use a different type of radiation for different type of cancers, right?
They will, absolutely.
So how do they know like which one?
Basically trial and error. So they look at what's worked in the past and then replicate it. So there are scientific studies that are done all the time on new techniques and so forth, which, looking at it from the outside, you may think is a very small change to see whether it helps or not. And then if it helps, then they'll do that. If it doesn't help, then they'll look for something else, and so on. So you look at the physiology of the cancer, what type of cells they are, how they're reproducing, things like that, but then also trial and error in terms of it. So whatever they find from that, then they'll try, see if it works or not, and then they move on. It's a very, very long process, sadly. In cancer, cancer just means an uncontrolled growth of cells. There's hundreds and hundreds and hundreds of different types of cancers. So, when people say we want to cure cancer, that's a huge, huge thing, because it's hundreds and hundreds of different diseases that all act differently and so forth, and then you've got to look at each individual one, such as treatment. And you've got to pick, this is this specific type, so then we've got to treat it in this way. Now there are some general things that they do that can be used in a lot of different types, but each one acts a little differently as it goes through it. Any other questions? No? Okay. So, we're going to talk about uses of radiation. Now, the two major uses that we're going to talk about in the rest of the course probably is medicine, and then nuclear power and weapons. Okay, so we'll look at those two in depth, but by no means is that all the uses of radiation. There's hundreds and thousands of them, probably hundreds in our daily lives that we can think of. So a few of them in smaller form, food, for example. A lot of foods are actually exposed to radiation in the processing phases, and the thought behind that is the radiation can kill off bacteria and small tiny organisms inside the food that lead to food becoming rotten. So food that's exposed to radiation in the process lasts longer. Vegetables, fruits, and so forth, meat in particular, it can kill off certain types of sicknesses associated with that. So a lot of times the food, as it's on its conveyor belt being packaged up, it will get exposed to radiation. This is very common and accepted in the United States. Most people don't even think about it in any way, shape, or form. Outside the United States, this is very contested in certain countries. France, for example, absolutely hates this approach that the United States uses. And because of that, you can't bring certain foods back from France. So fruits and vegetables, for example, when you come back from France, you can't bring them with you. I came back a few years ago. I went to Paris for a couple weeks, and I was traveling actually with an NKU group. They have a study abroad course that goes over and looks at the battlefields of France. I didn't do that, by the way. That's too gory for me. But we were traveling with them coming back, and we were coming through customs, and one of the dogs that they have there just went absolutely nuts. And the student's like, I don't understand. And they pulled the student out of line, and the professor went with them and everything. When they went into the little room to search them for contraband and stuff like that, the dog was just absolutely crazy. And what it was the dog was trained to smell fruit, because you can't bring fruits and cheeses and stuff back from France because of their processing of the foods. And it was, you couldn't bring fruit back. But the student didn't have any fruit. He had a fruit roll-up, and that was enough to trigger the dog and the smell and so forth. So it was all okay. They quickly released him back through customs, and he was able to join us and so forth. But they do actually look for it. I never in a million years would have thought there was dogs in the airport trained to smell fruit. That seems weird, but there are. And it's because of this whole idea of protecting food and so forth and our differing views about it. Nowadays, you can go to the store and actually find food that's not exposed to radiation on the labels and so forth, similar to organic, if that's the type of thing you care about. Tracers. Tracers are materials that are used to follow the path of something. This is the idea of it. So for example, I didn't draw this picture in class, right? No. Okay. I know I don't have the picture yet, but let's say we've got our house. You guys would remember my horrible picture drawings. Okay, there's our house. And we have a sewer line that runs out of our house. So down. And then it connects with this big sewer pipe under the house and under trees and so forth. Okay. So this is how it all normally works. And this is actually a very, very common thing to do. So imagine there is a hole in our sewer line and water is running out and causing us problems. How do we find where that hole is? Okay. Any ideas on how that's done?
Can you use a microscopic camera?
Microscopic camera will work. So what you would do is you would find something, an opening. So for example, if it's from a house, you may start at the house itself and start going. But it may be too far away from it because of it. So in the olden days, what they did was they would literally dig down and follow the pipe until they found the hole. This would be under houses, under sidewalks, under roads, under trees, all of these types of things. They would dig until they find it. But what they do now is they put a radioactive dye in the water, and that radioactive dye runs out, and then it collects at the break. So it collects there, and then from the ground, you go along and you measure the radiation, and when you get to the point of the break, it has a higher radioactive amount because that material is collecting there. So the radioactive material collects where the break is, and then you can measure that above ground. Yeah.
So that's similar to what they do with in certain heart procedures where they inject you with the dye.
Absolutely, and watch where it goes and so forth. The idea of tracers is very, very commonly used in medicine in a lot of different ways. Blood flow, heart motions, pumping of the blood and types of things like that. Bone density is another one they can do with it and so forth. So yeah, it's just, tracers is basically just following the path of something. So now you know where it is, you just dig down and you don't have to destroy the neighborhood to figure out and fix it. Yeah?
So like if you go ahead and you put the tracer in there, does it vary or does it depend on the thickness of how deep underground it is?
Yeah, in terms of the measurement and so forth, it would. But Geiger counters can actually be very, very sensitive. And you can put in basically as much as you want. I mean, yeah, within reason. So you can keep pumping it in until you can see where that actually occurs at and so forth. This is infinitely cheaper than trying to dig along the whole trench and so forth because of that. So yeah, but you are right. If it is really deep, then you're going to have a problem in terms of stuff getting in the way and so forth.
Like I wonder how long it would take. I mean, you have to wait a period of time after you go ahead and put the tracer in before you're going to, it's going to come to
Yeah,
the
but it would be
surface?
in like an hour or two.
Oh, that's
something
pretty
like
quick.
that. Not like days, because you're putting it in relatively close to the leak,
Right.
so it's there. I guess if it's a really small leak, it would take a while to collect. That may be a longer time, but it wouldn't take a super long time. This is, as I said, it's a fairly common technique in terms of finding holes, especially in underground sources and things like that, because you don't want to dig everything up. Especially if it runs under a street, then you've got all kinds of issues in terms of dealing with that. Okay. So this is a tracer. A tracer is, again, basically tracing the path of something. Yeah. I learned the term from bullets. They have bullets that will like glow as they're shot and mark the path. I'm not exactly sure how it works, but that's the same idea there in following the path of it as it goes through. Analysis of structural materials and so forth is another example. Over here, we're building the new nursing center. They have huge I-beams they're putting in place, and they want to make sure that those I-beams are good. So what they do is they basically use x-rays to image it and see if there are any faults inside of the beam. So imagine if there's a big hole inside of one of the beams, but you can't see it from the outside, okay, like a bubble, if you will. This would find that flaw relatively easily, and then they would get rid of that beam and use something else. So it's fairly common to do in terms of that. Structural integrity, those types of things as well. Airport security is becoming more and more common. For a long time, we've used x-rays. Now we basically have imagers, which are more like MRIs, where you walk in someplace and then it scans you and looking to see if you have any metal on you, not just a metal detector. These were really controversial a few years ago because of the image that it makes. And people were concerned about the images of their bodies and so forth. When they're looking for the metal, what kind of image is coming out of it? We also now have radiation detectors that measure radioactive material. So for example, at the Cincinnati airport, we have puffers. You walk in and it blows air on you, and then it collects the dust that comes off. You guys are aware of these? No, you've never done these? Oh, no, they have them there. I know they do.
Is this a new thing?
No, last 5-6 years, something, yeah.
Like, where do you have to go for that?
So, just like security clearance, it's a circle. It's like a circular thing, and you step in, and the door is closed, and it goes. I can even make the sound. It's little air flows, and what happens is maybe I don't know.
That's so, yeah, I've seen like the thing like you stand like that and it goes around your body, but I
Yeah.
haven't had like the air.
Not the thing where you put all your stuff in like the tubs and you walk
No.
through the little. Okay.
No, that's just a simple X-ray.
No.
Okay, maybe they took them out.
Yeah, I was there this June and I didn't see that.
I'll look into it now that I want to know. Next time I go fly somewhere, I'll ask them. That will make me not conspicuous at all. So what they are is it blows air on you and then it collects the dust that comes off and then analyzes it. So in the old days, they used to take these little, almost like cotton ball things and rub your bags, and then they would do the analysis. I know all this because I'm always concerned they're going to find something on my bags. Coming in and out of chemistry labs, there's a lot of chemicals that get exposed. So you rub and then you see what's there. So one of the things that they look for is radioactive material. When they collect the dust, they just look to see if you've been around radioactive material at all or not, for safety concerns.
But if you've gone through treatment in a hospital, you would not be, or would you still have some level on you?
You would not be. So this would be, it would have to be like those little discs I've got,
Right.
they have a little bit of radioactive dust inside of them. It would be looking for that type of stuff. So it would be more along the lines of nuclear waste or things along that. There's a lab we do, well, if you're in lab, you did it, where you do the half-life, the liquid part of it. If you got some of that liquid on you, then you could have radioactive material as well on you. But those types of things, not like radiation treatment. However, if you had a radioactive pellet inside of you, then you would set off the alarms. But you would have a note from your doctor. still stuck on this muffler though. Does anyone know what I'm talking about?
No.
No?
Can you pull it up like on YouTube or something so we can see if we've seen it or?
I probably can. I don't know what it's called though.
Airport puffer? That's literally what it is. That's crazy.
Okay. Well, I can look which airports use them. Cincinnati's not listed there anymore.
That's literally what it's called, just the airport puffer.
Yep. I don't see any images though. But basically what it is I know they used to be there. It just blew air on you and then collected whatever came off and then analyzed it. And that's how it worked. There's nothing really fancy about it at all. I feel like I'm wasting time on this. Okay. So those are all practical uses. I did list smoke alarms. Smoke alarms are by far the most common everyday use that we have for radiation. The idea that basically how a smoke alarm works is you have a radioactive material here. It's a beta. And then right next to it, you have the detector. And there's a little tiny beam of beta particles that go across. But when smoke gets in here, that blocks the beam. And because the beam is blocked, that's when the alarm goes off. And that's the way a smoke detector works. Very straightforward.
Do they use some like security systems the same way? If something comes in, like blocks the flow of the
You could. You absolutely could. Like if you move it or something like that.
Right.
But I don't know of any particular aspects of it, exact uses and stuff. Okay. Okay, other uses. Power generation. Okay. Nuclear power, we are hopefully all aware of this here on Earth. There are about 450 nuclear power plants around the world. We'll talk about that in more detail here in a minute. And then space-based. A lot of our satellites are actually based with nuclear power because once they get a little further out in the solar system, there's not enough solar energy to actually power them. So they use a radioactive material in there, they collect the radiation that comes off, converts it to energy, and then uses that energy to power whatever they need to power on the satellite. Basically anything going out of our outwards of our solar system is going to have some power generation from a nuclear source as it goes through it. This actually is the exact same way pacemakers inside the body are powered. They have a little bit of radioactive material. That radiation is converted to energy, and then that runs your pacemaker inside the body. You go through it. Okay, so looking at particular examples, the first one we're going to look at in detail is medical applications. And when you look at medical applications of radiation, that breaks down to two basic categories. The first is diagnostic, and this is where they're finding out what's wrong with someone. When you go into the hospital or to your doctor's office, something's wrong and they want to figure out what it is, this is the diagnostic portion. Okay. Then once they know what's wrong with someone, then it's a treatment, and radiation is used here as well. Yeah.
I'm sorry, I'm just curious
Okay.
on like the diagnostic part. Because now that you was talking about like there's multiple different cancers, how do they know if you have cancer? Do they test
So generally what happens, at least in my experience, is they take a sample of the cancer cells and then they look at them and analyze them to figure out what type of cancer it is.
so let's say you only have like lung cancer.
Okay?
So would they just take some of your blood? What do you mean like take
No, they would actually have an operation. They would go into where the tumor is located and physically take cells off of it.
So it'll start off as a tumor.
Yes.
Oh, okay.
Yes.
So, okay.
Generally, blood cancers maybe wouldn't have a tumor, but most types of cancers would have a tumor associated with it because that's the mass of cells growing that's causing the issue. So that's what they would sample, cells. And then pathologists would look at it, figure out what type of cells they are and so forth, and then do whatever they do.
Okay.
So radiation is all over different types of medicine and so forth. When we are looking at using radiation for medical applications, there are two main things that always have to be considered. The first is that whatever isotope you're using for your study must interact with whatever you're trying to study. Makes perfect sense. If you're trying to study your thyroid, for example, you need an isotope that will actually interact with the thyroid in some way. They always use iodine for the thyroid studies because iodine very heavily is associated with the thyroid itself. If you're trying to study the bones of somebody, you wouldn't use something that's just going to stay in the blood all the time and not go into the bones. Okay, so you have to make sure that the isotope you choose actually interacts with what you're trying to study. And then with that as well, it has to have an appropriate half-life. So if your study is only going to last for a day or two, you don't want to put radiation inside the body for the next 6 years. It just doesn't make sense to do that. So you want to match up your half-life as well as you can so you're not exposing to someone to radiation long-term when they don't need to be. The opposite of that is true as well. If you have a really long-term study, you may want to actually have a long-term isotope so that you don't have to keep injecting isotopic material inside the body all the time. It just kind of depends on the use. So it has to interact with it, and it has to have an appropriate half-life to work with. Here are some half-lives that common isotopes used. 28 days for chromium-51, and that's to study red blood cells and so forth. And then you got longer ones here. Iron is 450 days to study metabolism and so on. Now, for chemists, 10 half-lives is about the length of time. So the chromium we would think of as would be radioactive in the blood for about a year. Iron would be about 10 years in terms of that. So kind of depends on what you're trying to study as you're going through it in the cases. But it's really important, again. You don't want to do a one-day study with an isotope that has a half-life of 5 years, and then they've just got radiation inside their body for the next 50 years. I mean, it just doesn't make sense to do that if there's any other possibilities. Technetium, for example, is used a lot. Technetium is number 43 on the periodic table. It's used in a lot of different medical diagnostics and so forth. That has a half-life, I think, of about 6 hours. So it doesn't last very long. You have to order it specifically for each study as it goes through it. Now, another type of diagnostic that is used is the PET scan. Now, PET scan stands for positron emission tomography. Positron is another type of radiation that we didn't talk about in class. We have alpha, beta, gamma. Positron is another one, but we can just think of it basically as a beta type particle. It's got roughly the same properties as beta. But what happens in a positron study is you inject the patient with a material that usually has something. Here's an example of one. It has a radioactive carbon, carbon-11, and that's going to release a positron inside the body. Okay? So in the body, when this is released, gamma radiation is released, and then it can be measured from the outside. Now, it releases when generally a muscle is being used. So in x-rays, for example, if I break my arm and we do an x-ray, it takes an image of my arm being broken. Okay, that's a static image, if you will. It's just a picture of it. For positron, what it actually does is it maps work of muscles and tissues and so forth. So you can actually see the muscle working. So for example, you can do a study of the heart. And if one valve of the heart is not working like it's supposed to, you won't see the emission from that area. So you can see these images of hearts, and then certain areas don't have the muscle work, the muscle motion and so forth that it's supposed to have, and it's dark on the images. So imagine the rest of the heart's lit up like normal, and then there's one dark area on a valve that's not working properly. So then they can go in and know exactly where to look for valve replacement or repair or something along those lines. The example I chose in terms of this for the class is brain mapping. I think this is absolutely amazing in what's done here. So what occurs is the patient is injected with this radioactive material, and it runs through the body and gets into the brain, and then they study the brain's activity under certain conditions. So here, for example, are some static conditions. Here is the brain activity of a non-smoker versus a smoker. So generally brighter means more activity. So you see depressed activity, a depression of activity, I should say, depression of activity inside the smoker. Normal versus alcoholic. Here, again, you see a decrease of activity. You do actually, in this image at least, see an increase right here in the brain versus right there. Not sure if it's significant or not, but it's an interesting little blip there that you're seeing more activity in that case. Normal obese, addicted to cocaine, and then normal as well. So you can actually start mapping out how these different conditions affect brain activity, okay? And seeing what their outcomes are in terms of it.
I have a question.
Yeah.
There was something recently, I didn't get to see all of it, I don't know if you caught it, but they were talking about some breakthroughs with Alzheimer's and being able to treat it with something that was a lot more common than we thought. I don't know if you had heard anything about that or.
No. I know that I just caught a glimpse of 60 Minutes, or one of those news shows, was doing a story on Alzheimer's.
Right.
And in the preview, they actually had someone doing a PET scan. They had an image of someone doing a PET scan. Alzheimer's is something that PET scans have done a lot with, because they believe that's coordinated to activity in the brain and so forth, so that way they can directly map it as they're going through. But I don't know about the study that actually is the treatment and so forth. Hopefully we can get to the bottom of it quickly, more quickly. I remember when I was in undergrad, I went and visited a professor that was working with Alzheimer's back then. So, yeah, I'm hoping for more progress in terms of that. So this maps activity, especially with addictions to certain things. Another study that was done actually looked at pain, and this is one of the very first types of study like this. So volunteers, and they were told ahead of time what the study was. They weren't just blindly volunteering. They were injected with what's called capsaicin. Capsaicin, you may be familiar with the name of it. It is what makes hot peppers hot. But apparently, and I don't know this and I'm not volunteering to test this in any way, shape, or form, if it's injected into the body, it's like the worst pain in the world. Like unbelievable pain. Like instantly as bad as it could be. I don't even know how to describe it. Okay? But what they did was they put the chemical inside the body, and then they injected the people with capsaicin and then marked the brain where the pain activity was. And they were able to map out the parts of the brain that correspond to pain and so on. And they've done this with other things as well. Yeah?
So wait, how's that different from like a lethal injection?
So this didn't actually kill them.
But, so what hurts? I mean, you probably don't know, but what hurts more? If something kills you compared to something that just
Okay.
pain?
I'm going to go with the scientific answer to that, not the philosophical answer to that. Okay? In a lethal injection, before they do the lethal injection, they actually give you chemicals to basically turn off pain inside the body, which is one of the big reasons why the shortage of chemicals for lethal injections right now in the United States is such a big deal, because they were using a cocktail that basically numbed out the pain, and they can't do that right now because of the availability of chemicals, so they can't do lethal injections in a lot of states. So I would say that this would be more painful than that because that specifically turns off pain. In terms of the philosophical aspects and so forth, lethal injection would obviously be much, much worse in my opinion. But in terms of actual physical pain, then that's what it is. And I don't know why it causes the pain, I just know that it does. I remember once I saw, do you guys remember this show, House? It used to be a relatively popular show. There was one time he was trying to fake someone was, he was trying to prove someone was faking that they couldn't feel things. And he went up behind him and just jabbed him in the arm with this needle and injected something, and apparently he was supposedly injecting capsaicin in him. But, you know, I don't understand the science of it at all.
So what's the point?
So the point in this case was to have the parts of the brain that coordinate to pain light up because of the activity of it. And they were able to do that. When I was a kid, we learned about this guy who had like a railroad spike through his head or a metal rod through his head, and his personality changed. And this was a real thing. So this guy was in an accident, and let's just go with a metal spike. And he had a metal spike that went through his brain, but he didn't die. He actually stayed alive. And because of this accident, his personality changed. And this started scientists to think about what parts of the brains were actually injured in this and how that affected his overall personality. So now they do studies like this, where they have people in a PET scanner and they have them do mathematics problems. 2 + 2 is 4. 4 - 3 is 1. And then they look at what parts of the brain are actually being activated for these types of things. Think about your happiest memory as a kid. And then they see what part of the brain associates with happiness. Think about your saddest memory, and they associate that. So because of these studies, they've actually been able to map out different areas of the brain and see what corresponds to what. Again, when I was a kid, we learned that half of the brain, the right half and left half, corresponded to different things. So one half of the brain corresponded to math, the other half was creativity. These studies have shown that that's not true at all. When you're doing math, there are different areas of your brain all over your brain that are being activated. When you're thinking about happy thoughts, different parts are happy. You know, when you're hearing a poem, different parts of your brains are. It's not just simply right and left, it's different areas all over the place.
What do they mean by, and I don't know if this is even a factually true statement, but you hear it a lot. We only use 10%, or we only use a portion, like the full capacity of our brain. Is that, how has that been determined? And like if they say, you know, you look at a scale like this and everything lights up and you believe that, all right, well, the non-smoker that's just an average Joe Blow, that look like they're using most of their brain, but how do they determine only a certain percentage is used?
Okay, I think, from my understanding of it, and I don't exactly know the answer, but from what I believe, they're not basing that on area, so to speak. I think it's based on the neurons and the amount of neuron activity. Yeah, do you know?
There was a study that, like, it's not exactly true that you only use 10% of your brain. Your brain, you actually use all of it all the time because you need all of your brain to function throughout life. They did a study on that to disprove that the 10% is not real.
Where did that even come from then? I mean, it was just...
It was just for like a motivational thing.
Oh.
Like
so
fire
like,
people up?
you don't use 10% of your brain, be sure to use all of it. And like, it was
I
just-
never knew that.
Yeah.
I gotta look that up. I guess that's, I mean, when I was a kid, we were taught left brain, right brain, and that was a thing. Like, I don't know if you guys learned this or not, but that was how the brain was set up. Half the brain was for math, half the brain was for creativity. You were a left brain person or a right brain person, whether you're good at math or you're good at creative things. Never the two shall meet. Okay, but that's not true at all. Right brain, left brain has been completely disproved. I guess like the 10% from studies like this.
So is it just an excuse if someone says, hey, I'm just not good at math, or I don't have an aptitude, or? No, I don't think so. I think that different people have different skill sets and so forth.
but there's no reason why someone who's good at, and actually I would bet thousands and thousands of dollars if you looked at it. People who are good at math are not excluded from being good at art, and vice versa. I mean, if you look at Da Vinci, some of his sketches and stuff are very, very artistic, but they're also very mathematical. So that would be both sides there in terms of that. So I think that whole theory is just wrong, so to speak. But it was an absolute, well, it wasn't an absolute fact, but it was a scientific accepted fact for a long time. So these types of studies have shown that that's not the case. And different parts of the brain then correspond to different things. And you can see and really map out the brain three-dimensionally exactly what areas are responsible for what feelings and so forth. And I find that really, really cool. And how they do that's amazing. Okay, so the last thing then that I'll mention today is treatments. So moving over, once you've figured out what is wrong with the person, you have to treat the person for whatever the issue is. And here, by and far, the biggest form of radiation treatment is the fighting of cancer. Now, the reason why this is so important in the fighting of cancer is the fact that cancer cells grow very fast. That's, by definition, what a cancer is. It's a fast-growing, uncontrolled growth of cells. The faster cells grow and reproduce, the more susceptible they are to radiation. So we see this in our own bodies if we're exposed to radiation. For example, our stomach lining is very, very fast-growing cells. So people who undergo radiation treatment often have problems with their stomach and so forth. Hair and nails are another example of this. Those are some of the fastest growing cells in our body. When you undergo radiation therapy, you lose your hair generally. That's a very common side effect to it because of the way that radiation interacts with those cells. Cancer, fast growing cells, we use this to our advantage by exposing it to radiation to kill them off. Now normally, this isn't the only thing you do. You do radiation, you do chemotherapy, which is therapy based on chemicals, which ideally is poison for the cancer cells, and then you also have surgery associated with it. You do all of the above to try and help yourself in terms of it, but radiation is incredibly common in the treatment of cancers. This radiation source, as I already said, may be external, where they're shooting a beam of radiation at a person. Then they've got to consider what else is present there. Inside the chest cavity, for example, this could be particularly difficult because of the beam and the pathway may pass through multiple organs and so forth. Or it may be internal, where they actually put a radioactive material inside the body. And then that radiation damages the cells right there. Questions about that? No? Okay, so that leaves us for next class period with nuclear power and nuclear weapons. So we'll get started on that next time. I don't want to jump into that with only a few minutes left. So I hope everyone has a good day. And lights, I'll see everyone Thursday then.